In this video, we're going to take a look at matrices and matrix operations. So a matrix is an array of numbers. It's going to have rows and columns, and it can have any number of rows and any number of columns. Now, the number of rows and the number of columns make the dimension of the matrix. We say that an M by N matrix is a matrix with M rows and N columns. We call M and N the dimensions of the matrix, and we always list the rows first and the columns second. You'll also see this called the size of a matrix. So the dimensions or the size of a matrix. In the matrix we looked at just a second ago, we can state the dimensions. So this first matrix has 1, 2, 3 rows and 1, 2 columns. So this first matrix in the upper left is a 3 by 2 matrix. It has 3 rows and 2 columns. In the upper right matrix, this matrix has 2 rows and 3 columns. So we say this is a 2 by 3 matrix because of that. This matrix in the lower left has 3 rows and also 3 columns. So it is a 3 by 3 matrix. This matrix has 1 row and 3 columns. So it's a 3 by 1 matrix. Now, when the number of rows and the number of columns are equal, we call that type of a matrix a square matrix. So the 3 by 3 matrix we saw on the previous slide, we would call a square matrix. If we have a matrix with every entry being the number 0, we call that an M by N 0 matrix. So the 0 matrix has all zeros. A square matrix has the number of rows and the number of columns equal. Other notation that we often use, oftentimes we use a capital letter for a matrix. And then the individual entries are denoted by the rows and the columns they are in. So for instance, this entry, the 2, 1 entry, is in row 2 and column 1. The 2, 3 entry is in row 2, column 3. And the 3, 1 entry is in row 3, column 1. So that's how we denote the entries in a matrix when we don't know the specific numbers that they are. And what we're going to do now is we're going to start doing operations with matrices. The first operations that we're going to look at are the operations of addition and subtraction. When you add two matrices, you add them entry-wise. When you subtract two matrices, you subtract them entry-wise. So here we have two 3 by 2 matrices. And when we add them, notice that the 1, 1 entry of matrix 1 added to the 1, 1 entry of matrix 2 gives me the 1, 1 entry of my resulting matrix. So 5 plus 2 gives me 7. 7 plus 0 gives me 7. 2 plus -8 gives me -6. -1 plus 1 gives me 0. -3 plus 4 gives me 1. 6 plus 4 gives me 10. So we add them entry-wise. Notice that these two matrices have the same dimensions when we added them, and they resulted in a matrix with the same dimensions. 3 rows, 2 columns, to be specific. The same thing is going to work with subtraction. I'm going to subtract entry-wise too. 2 subtract 6 gives me -4. 3 subtract 1 gives me a 2. 1 minus 1 gives me a -2. And 7 minus -4 gives me a positive 11. Again, when we subtracted the two matrices, they had the same dimensions, and the resulting matrix had the same dimension as well. Now, what if the dimensions don't match up? What if we have a 3 by 2 matrix added to a 2 by 3 matrix? Well, it turns out if matrices don't have the same dimensions, then we cannot add and subtract those matrices. So in a case like this, we don't try to add 2 and 1 and try to make some other dimensions up. We just say these don't have the same dimensions, therefore adding is not a possibility. Or the sum does not exist. Another operation on matrices that we have to look at is the operation of scalar multiplication. When I say scalar, that just means a real number that we're going to now multiply by the matrix. When I multiply a number times a matrix, I get the resulting matrix out as just each entry multiplied by that number. So 4 times 5 gives me 20. 4 times 7 gives me 28. 4 times 2 gives me 8. 4 by -1 gives me -4. 4 by -3 gives me -12. And 4 times 6 gives me 24. We can do that with other dimension matrices as well. It doesn't matter what the dimension of the matrix is. You simply add the or multiply the coefficient times every entry in the matrix. So that's how we do scalar multiplication. I have a number multiplied times a matrix, and I multiply that number times each entry of the matrix. So let's do an example where we have to use the rules of matrix addition, matrix subtraction, and scalar multiplication to simplify and rewrite the following matrices. Go ahead and push pause on the video. Try this on your own. In a couple of seconds, I will show you how it's done. All right, in both of these problems, we have the same dimensions on the matrices. So in this first problem, both matrices have 3 rows and 2 columns. So I can add them, and I just simply add them entry-wise. So obviously 4 plus 1 gives me a 5. 9 plus a -8 gives me a positive 1. 12 plus a -3 gives me a 9. 3 plus 14 gives me 17. -10 plus 2 gives me a -8. And 15 plus a -5 gives me a positive 10. All right, so that's how to do that first problem. In the second problem, it's the same. We take 1.8 minus a negative 6.3. That becomes 8.1. 3.3 minus a negative 3.7 becomes a 7.0 if I want to write the point zero. Negative 4.1 minus 6.1 is negative 10.2. And 2.8 minus 1.5 gives me a positive 1.3. So I get this matrix. Now notice that in both cases, we're adding matrices of the same dimension and we get out an output matrix of that same dimension. Sometimes people, instead of trying to do a subtraction, sometimes people will do an addition and then just change the signs on each number inside. In other words, they will distribute the negative to the inside of the matrix, and they'll put a negative on every single entry on the inside of the matrix. Either way is perfectly fine to do that. Let's do another couple of examples. Let's simplify these using matrix operations. Go ahead and push pause on the video and try this on your own. In a couple of seconds, I will show you how it's done on the video. For this first one, where we're supposed to add two matrices, since these do not have the same dimension, the sum of those two matrices does not exist. So one is a 2 by 2, the other is a 2 by 3. We cannot add matrices of different dimensions, so the sum there does not exist. For this second problem, all we'd have to do is take each one of these entries and multiply by 6. So 1.8 times 6 is 10.8. 3.3 times 6 is 19.8. Negative 4.1 times 6 is negative 24.6. And 2.8 times 6 is a 16.8. So that's the scalar multiplication of a matrix. Let's do one more example. In this example, it asks us to do simplification. We're going to combine and we're going to write our answer as one matrix. When we do that, notice that this is going to require us to do scalar multiplication and matrix addition or matrix subtraction, depending on how I do my scalar multiplication. So this is going to have a couple of steps. Push pause on the video if you want to try this on your own. In a couple of seconds, I will show you how it's done. All right. Now, what I'm going to do is I'm going to do a scalar multiplication and then addition. In fact, that's what we have to do because of order of operations. Multiplication comes before addition. So we do a scalar multiplication of our first matrix. 3 times every entry gives me negative 12 in the first row, first column entry. It gives me an 18 in the first row, second column entry. It gives me a 36 in the second row, first column, and it gives me a 39 in the second row, second column. Now, there's a couple of ways to do the scalar multiplication on the right-hand matrix. You could multiply 2 times everything and keep the minus sign out front, or you could multiply everything by a -2 and change that minus sign to a plus sign. That's what I'm going to do. So -2 times 3 means that -6 is in the 1, 1 entry. -2 times 1 means that -2 is in the 1, 2 entry. -2 times -1 means that 2 is in the 2, 1 entry. And -2 times 5 means that -10 is in the second row, second column, or 2, 2 entry. After I've done that, then I can add. So -12 plus -6 is a -18. 18 minus 2 is a positive 16. 36 plus 2 is a positive 38. 39 minus 10 is a positive 29. So that is the final matrix, simplified as much as I can make it. It's a 2 by 2 matrix with the entries -18, 16, 38, 29. So that's how we do scalar multiplication and addition of matrices. Remember, if we're adding matrices, they have to be of the same dimension. Now, the operation that's most unique with matrices is matrix multiplication. If we're going to multiply one matrix times another matrix, what we do is the product of row M of the first matrix, which is also called the lead matrix, will multiply with the column N of the second matrix, and that will produce entry AMN of the product matrix. So the row of the first matrix multiplies times the columns, the rows of the first matrix multiply times the columns of the second matrix. Now, let's explain that in a 2 by 2 matrix times a 2 by 2 matrix example. So what's going to happen here is I'm going to take the row which contains -4, 6. That's the first row of my lead matrix. And it's going to multiply times 3, -1. That's the first column of my second matrix. So row 1 times column 1 is going to result in the 1, 1 entry. Now, the way we multiply is I take -4 times 3 and then 6 times -1. Most people think of this as taking your first row and rotating it 90 degrees and then multiplying it times 3, -1. -4 times 3 is -12 plus 6 times -1 becomes a -18. So that becomes a -18. And then I move on and I take the first row times the second column. So -4, 6 times 1, 5. -4 times 1, 6 times 5. -4 plus 30 will become 26. Again, first row times second column is going to give me the 1, 2 entry. Now notice that after I do this, I'm out of columns to multiply times that first row. So then I'll move on to the second row and do the exact same thing. Second row times first column, that's 12 times 3. plus 13 times negative 1. That'll be 36 minus 13, which is 23. And then I will multiply the second row by the second column, 12 times 1 plus 13 times 5. That gives me a 77. So when I multiply these two matrices, I got negative 18 as the 1, 1 entry. That came by multiplying first row times first column. 26 as the 1, 2 entry. That was first row times second column. 23 as the 2, 1 entry. That's second row, first column. And then 77, that's second row, second column. So the 2, 2 entry. So that's the gist of how matrix multiplication works. I take each row in the lead matrix or the first matrix, and I multiply it times every column of my second matrix. So let's go ahead and do an example. Here we're taking these two matrices and we're going to multiply them. Notice that I don't have the multiplication symbol here. Anytime we have two matrices right next to each other, it's going to be implied that we are multiplying. So go ahead, push pause on the video if you'd like, and do these problems. I will show you how each is done in a couple of seconds. Now, I'll talk about the dimensions in a moment, but basically, since we have a 2 by 2 matrix times another 2 by 2 matrix, our resulting matrix is going to be 2 by 2 as well. So let's go ahead and do the multiplication. I'm going to take my first row, 3, 5, times my first column, 8, negative 4. That's going to be 3, whoops, 3 times 8 plus 5 times negative 4. That's going to be my first entry in the 1, 1 entry, first row, first column. Then I'll go first row, second column. That will be 3, 5 times 4, negative 6. So 3 times 4 plus 5 times negative 6. Then my first row has multiplied times all of the columns. So then I move on to my second row. My second row is going to multiply the first column, first column of the second matrix. We go 1 times 8 minus 2 times negative 4. That'll give me the 2, 1 entry of my resulting product. Then I'd take 1 times 4 minus 2 times negative 6. Again, that's second row in my lead matrix times the second column in my second matrix. And then I simply calculate what each of these numbers is. 3 times 8 plus 5 times negative 4 is a 4. Again, 24 minus 20. Then I get 3 times 4 plus 5 times negative 6, 12 minus 30, which is negative 18. 1 times 8 minus 2 times negative 4, that's 8 plus 8, which is 16. And then 1 times 4 minus 2 times negative 6, That's 4 plus 12, which is 16. So I get that matrix when I multiply 3, 5, 1, negative 2 by 8, 4, negative 4, negative 6. Now the second problem, we just multiply those two matrices in the reverse direction. I'll go a little bit quicker now. First row, 8, 4 times first column, 3, 1 gives me 8 times 3 plus 4 times 1. Then 8, 4, first row, we'll multiply by second column, 5, negative 2. That's 8 times 5 plus 4 times negative 2. Then I move to the second row. Second row times first column is negative 4 times 3 minus 6 times 1. And then lastly, second row times second column is negative 4 times 5 minus 6 times negative 2. When I add everything up, 3 times 8 plus 4 times 1 gives me 4 plus 4, which is 28. 8 times 5 plus 4 times negative 2 is a 32. That's 40 minus 8. I get negative 12 minus 6, which is negative 18. And then negative 20 plus 12 becomes a negative 8. Now I want to point out the very obvious thing here is that these two are just we're multiplying the matrices, but in a different order. The 3, 5, 1, negative 2 was the matrix on the left in the first multiplication. That matrix is the matrix on the right in the second multiplication. 8, 4, negative 4, negative 6 is the matrix on the right in the first multiplication. It's the matrix on the left in the second multiplication. And we got out different matrices depending on which matrix I put on the left and which matrix I put on the right. So what that means is that matrix multiplication in general is not commutative. A times B, matrix A times matrix B, is not equal to matrix B times matrix A. That's what we're stating right here. However, when we did the addition, that was commutative. Adding two matrices, since we were doing it entry-wise, worked out as commutative. But multiplication, we have this weird algorithm of row 1 times column 1, row 1 times column 2, and so on and so forth. So that does not lead to commutativity in general. So in general, matrix A times B is not equal to matrix B times A. Now let's take a look at dimensions. In the first example, all of our matrices were 2 by 2. So let's do another example where we try to multiply matrices, but this time they are different dimensions. Here we have in the first case, we have a 2 by 2 matrix multiplied times a 2 by 3 matrix. In the second case, I have a 2 by 3 matrix multiplied times a 2 by 2 matrix. If you want to try these on your own, go ahead and push pause on the video, see what happens. Otherwise, I'll show you how to do it in a couple of seconds. All right, now let's check out this first multiplication. We have a 2 by 2 matrix. So that means when I look at the first row, it has 2 entries. I can flip that 90 degrees and multiply by this first column because this first column also has 2 entries. And then I can multiply by the second column, and then I can multiply by the third column. So notice that we can do that because the number of entries in a row is equal to, in the first matrix, is equal to the number of entries in the columns of my second matrix. So if you do the thought process, you'll see that this is going to lead to 3 columns because each time I take that first row times a column, I can get a new entry. So I'm going to get 3 entries when I multiply the first row. And then when I multiply the second row, I'll also get 3 entries. So I'm going to get a resulting matrix, which is 2 by 3. So let's go ahead and do that. First row times 2, -7 is going to be -4 plus 7. I'm multiplying in my head there. -2 times 2 is -4. -1 times -7 is a +7. Then I'll take -2, -1 times 4, -2. That's -8 plus 2. And then in the third entry of the first row, -2, 1 times 3, 0. -2 times 3 is -6. -1 times 0 is 0. So that's -6 plus 0. Then I do the same process for the second row. 1, 5 times 2, -7 is going to give me 2 minus 35. 1, 5 times 4, -2 gives me 4 minus 10. And then 1, 5 times 3, 0 gives me 3 plus 0. So the resulting matrix there is 3, -6, -6. That's the first row. And then the second row is going to be -33, -6, and +3. So there we go. We've multiplied a 2 by 2 matrix times a 2 by 3 matrix, and we got out a 2 by 3 matrix. Now, what's going to happen in the second case? By the way, if we call this first matrix A and the second matrix B, then this one is B times A. So if I try to multiply this, since I have 3 entries in a row, but only 2 entries in this column, the numbers don't match up. This is 2 by 3, this is 2 by 2. So because if I tried to multiply, I'd multiply 2 times -2, then 4 times 1, and then I'd have a 3 left over that I can't multiply by anything. So in this case, the dimensions don't match up in the way that I can multiply them. Now, let me just mention a couple of things about dimensions here. I want you to understand in this first example, it was 2 by 2 multiplied by a 2 by 3 matrix. And that gave me a 2 by 3 matrix. Okay. In the second one, the dimensions were 2 by 3 multiplied by 2 by 2, and that did not exist. Now, the key thing is that these middle dimensions matched up in the first case, and in some way, they kind of canceled each other out. So the 2's in the middle matched up and they canceled each other out. Here, we had a 3 matching up with a 2. The number of columns is the number of entries in a row. That needs to match up with the number of rows in order to multiply, in order to be able to multiply. So that's the idea. As long as these middle entries match up, then I can do matrix multiplication. And if these middle entries don't match up, so if the number of columns in the first matrix doesn't match up with the number of rows in the second matrix, then I cannot multiply the two matrices together. When they do match up, they're going to cancel each other out, and I'm just left with a 2 by 3 matrix. Now, that's exactly what happens in general. When we're multiplying matrices, the number of columns in the first matrix must be equal to the number of rows in the second matrix. And the way the dimension behavior works is that if I have m times n matrix multiplied times n times p matrix, notice the columns in the first matrix match up with the number of rows in the second matrix, then these two will cancel each other out and we'll be left with an m by p matrix in the end. So that's how the dimensions work with the ability to multiply two matrices together. Now, let's do another example. Let's multiply this 3 by 3 matrix by this 3 by 3 matrix. We don't want to just have 2 by 2's all the time or 2 by 3's all the time. Let's do a 3 by 3 multiplied by a 3 by 3. We know the dimensions match up in the middle. There's 3 columns in the first matrix, 3 rows in the second matrix. So the multiplication will exist and it'll give us a 3 by 3. That's the nice thing about square matrices. When we do multiplication of a square matrix by another square matrix with the exact same dimensions, we get out a square matrix with the exact same dimensions. So go ahead and push pause on the video. Try this on your own if you like. And in a couple of seconds, I will show you how it's done. All right, so the first thing we're going to do is take row 1 of the first matrix times column 1 of the second matrix. 2 times 8 becomes 16. -3 times 0 is a 0. And then 1 times 7 is a 7. So when we add those up, we end up with the number 23. For the 1, 2 entry, that's row 1, column 2, We'll multiply the row 1 of the first matrix times column 2 of the second matrix. 2 times 0 is 0. Negative 3 times negative 1 is a positive 3. And then 1 times negative 9 is a minus 9. When we combine those, we get a negative 6. Then we'll take row 1 times column 3. 2 times negative 4 is negative 8. Negative 3 times 2 is a negative 6 or minus 6. 1 times 5 is 5. That is giving me negative 8 minus 6 plus 5 gives me a negative 9. Now we got to go to the second row. Second row times first column, 0 times 8 is 0. So second row of the first matrix times first column of the second row of the first matrix times first column of the second matrix. So 0 times 8, 4 times 0, negative 6 times 7. So 0 plus 0 minus 42. That's obviously a negative 42. And then we move on. Second row times second column, we get 0 times 0. 4 times negative 1. And then negative 6 times negative 9. That's going to be a positive 54. So we get a positive 50 as the 2-2 entry. And then second row times third column, 0 times negative 4. 4 times 2. Negative 6 times 5 gives me 0 plus 8 minus 30, which is a negative 22. Now I'm ready for the third row entries. So I take third row, maybe I'll just highlight this for right now. Third row times first column, negative 3 times 8, negative 24. 4 times 0 is 0. And negative 1 times 7 is negative 7. And then I'll do third row times second column. Oh, by the way, that's a negative 33, or excuse me, negative 31 when I add those. What is that now? So now we'd have negative 3 times 0, 4 times negative 1, and negative 1 times negative 9. So that's 0 minus 4 plus 9, which is a positive 5. And then lastly, third row times third column. Negative 3 times negative 4 is a positive 12. 4 times 2 is a positive 8. Negative 1 times 5 is a minus 5. So that's 20 minus 5, which is a positive 15. So there we go. So when I multiply this 3 by 3 matrix times this 3 by 3 matrix, I get out a 3 by 3 matrix. And this is how I go about doing all of that. And like we showed, each entry is a row of the first matrix times some column of the second matrix. So for instance, when I take row 2 times column 3, that gave me the 2, 3 entry of my resulting matrix. 0 times -4, 4 times 2, -6 times 5 gave me that. And you can do that with any row, any column. Now, the last thing I want to do is demonstrate how multiplication and addition of matrices interact. We'll deal with all 2 by 2 matrices, and what we'll do is 2 different problems. We'll take a matrix times the sum of 2 matrices, and then I'll take that matrix times the first matrix and then add it to the matrix times the second matrix in the sum. So we'll do the sum first and then multiply, and then we'll multiply the first matrix in the sum by my matrix outside, and then multiply the second matrix in the sum by the matrix outside, and then add them and see what happens. If you want to go ahead and try this on your own, push pause on the video. In a couple of seconds, I'll show you how it's done. All right, so let's go ahead and do this. This first matrix, the one that's acting sort of as our coefficient matrix, is going to stay outside, and I'm going to add these 2 matrices inside. 7 plus 5 gives me a 12. 0 plus -1 gives me a -1. 3 plus -2 gives me a 1. 2 plus 4 gives me a 6. So if I add the 2 matrices inside of the parentheses, then the matrix inside of the parentheses is going to be 12, -1, 1, 6. Then I would multiply. And if I multiply a 2 by 2 matrix times another 2 by 2 matrix, I'm going to get a 2 by 2 matrix. We know how to do this to get the first row, first column. I take first row times first column. That's going to be -1 times 12 plus 0 times 1. That's -12. And then first row times second column is going to give me a +1 plus 0. And then I move on to the second row. Second row times first column. I won't do the circling every time, but 1 times 12 plus 2 times 1. And then second row, second column is going to give me -1 plus 12. Let me just clear those. So we end up with a final answer of a 2 by 2 matrix whose entries are -12, 1, 14, and 11. Now, what if we would have multiplied this matrix times 7, 0, 3, 2, and then this matrix times 5, -1, -2, 4, and then added. Let's go ahead and do that. So I'm going to multiply the two matrices first and then add. Now I'm going to do this quickly. In the first case, -1 times 7 is a -7, plus 0 times 3, that's a 0. So I just get -7 in the first entry. In the 1, 2 entry, -1 times 0 is 0. 0 times 2 is also 0. 0 plus 0 is 0. In the 2, 1 entry, I'd get 1 times 7, which is 7, plus 2 times 3, which is 6. 7 plus 6 is a 13. And then 1, 2 times 0, 2. 1 times 0 is 0. 2 times 2 is 4. So I'll get a 4 there. In the next multiplication, -1, 0 times 5, -2. -1 times 5 is -5. 0 times anything is 0. So I get -5 as my 1, 1 entry. -1 times 1 plus 0 times 4 is a positive 1. So that's my 1, 2 entry. 1 times 5 plus 2 times -2. That's 5 plus -4. That's going to be a 1 as my 2, 1 entry. And then 1 times -1 plus 2 times 4. That's -1 plus 8, which is a 7. So I get these two matrices that I need to add up. Adding these up entry-wise is going to give me -12, 1, 14, and 11. Now, obviously, these two answers are exactly the same. And this is a demonstration of the distributive property. If I want to add two matrices and then multiply by a matrix on the outside, then I could have multiplied that matrix times each individual matrix on the inside. It would have given me the same result. Now, this doesn't happen just in this case. This will happen in general as long as the dimensions all make sense. In other words, if I can add these two matrices up, and if I can multiply this matrix times the sum, or if I can multiply this matrix times each individual matrix, and then add them up, as long as the dimensions match up, then that distributive property will hold. Now, another property that actually holds that I did not demonstrate is the associative property. If I have three matrices, if I take A times the product of B times C, or if I take A times B as a product and then multiply times C, then I'm going to get the exact same result. This is the distributive property of matrices. If I have A times the quantity B plus C, that's going to be equal to A times B plus A times C, as long as all the operations work. Now, I do want to point out something. In all of these cases, or in both of these cases, it is important which side I have the A on and which side I have the other matrices on. You'll notice when I distribute, since this A started on the left-hand side, this A and this A both need to be on the left-hand side. Because if I flip the order, if I take C times A instead of A times C, then I'm not going to get the same matrix because of commutativity, or because of non-commutativity, I should say. So we do get an associative property with matrix multiplication. We do get a distributive property with matrix multiplication, but we have to be very aware on which side we're multiplying. If the A is on the left-hand side, then the A needs to stay on the left-hand side when I distribute it. The same thing is true with associativity. If the order goes A, then B, then C, then over here I still need to do A, then B, then C from left to right, although I can do my multiplication in whichever order I want, as long as the A is always on the left and the C is always on the right. Hopefully that makes sense. By the way, you may ask, well, what happens if A is on the other side? If A were on the right-hand side of the B plus C in parentheses, then we just distribute it the other way. So if A was on the right, we could still distribute, but we'd have to keep the A on the right-hand side when I distribute. So this distributive property that we know from real numbers holds true in matrices as well, as long as I keep the A on the correct side. And that's all because, remember, in general, A times B is not equal to B times A. So if I throw the A on the wrong side, then I may get a wrong answer. Again, matrix multiplication in general is not commutative, but it is associative, and it does abide by the distributive property as long as the dimensions match up. Now, there's one last thing I want to say about matrices and matrix operations. If you are utilizing a graphing calculator, then most graphing calculators have a way to do all of these operations on matrices via a matrix menu. And I will add another video to show you how to add, subtract, do scalar multiplication, and do multiplication of matrices on that TI-84. So I'll do another video with the TI-84. It's good to know how to do these operations by hand, but sometimes it's good to have a calculator check our answers as well.